Buses. In this nugget, we talk about buses. As we talk about buses, we'll start off with a discussion of various terms relating to buses that are also very important in terms of calculating the overall bandwidth of one of the buses. When we talk about buses, there's several types. There's PCI buses, there's PCI X buses, which are actually normally in servers, and then there's the common PCI Express, which we're seeing on almost anything that's new these days. These are different ways of expanding to put in expansion cards into your system. Some of the other types of expansions that you might see will be for video, AGP, which is accelerated graphics port, and then also TV cards, which you might see following any of these kinds of standards earlier, that they might have an interface that plugs into one of these PCI slots, for example. You'll also have AMR and CNR slots, and these are audio modem risers and communications network risers. And then we'll finally conclude with a discussion of the old antiquated modem, which some people will still have to use for various purposes, but which is largely defunct nowadays. Have you ever felt like you just did not have the bandwidth to be able to get everything done? Certainly that was the case with me. I had a busy week, and I knew there was something I forgot. And then I woke up this morning, which is Sunday, February 14th, and guess what I forgot? Yeah, you got it. Valentine's Day is today, and I didn't get my wife a Valentine's Day card. So I quickly ran down to the Walmart under the guise of going to Starbucks to get her coffee, and I went to the entryway, and Walmart was thinking ahead. They have all of the Valentine's Day cards for us neglectful husbands right there. In fact, I think they should just rename Valentine's Day to Bad Husband's Day. Anyway, they had all these Valentine's Day cards right there in the entryway so that I could pick something out without even having to go all the way to the card section. And although they were kind of tattered and picked through, I finally got one while everyone was kind of staring at the back of my head as they were walking into the store. They were probably saying to themselves, boy, he's a bad husband. He didn't get his wife a Valentine's Day card until now. So anyway, I went and got also a bag of chocolate. Yes, that's how cheap I am. Not even a box of chocolate, a bag of chocolate. And I brought it home, and I'm sure my wife was very pleased with everything I got her. Was able to do the whole thing for less than $10. Well, as pleased as I was with myself, it turns out that she had been thinking ahead, and guess what? She got me a Valentine's Day present. I didn't even get her a present except for that bag of chocolates. This, folks, is what she got me. Yes, I'm wearing it on my arm right now. A really nice, hugely expensive watch. I just couldn't even believe that she, got me this. So I was very, very pleased with it, but boy, I've got about a year's worth of guilt to live up to now. Anyway, I do hope that you all have enough bandwidth to get the things done that you need to get done. But when it comes to bandwidth and calculating the bandwidth, we first of all have to understand terms that are relative to it, because it's all really just about math. The first thing to understand is megahertz. That's the abbreviation you'll see for it, capital M, capital H, lowercase z, and that is for megahertz. Okay, let's kind of parse this out, because this is actually two words that you can derive the full meaning of what megahertz means. We'll parse it out. Sounds like we're back in grammar school, huh? So anyway, with megahertz, mega equals 1 million. Okay, that's what mega means, 1 million. Our hertz is a cycle. Okay, and in computing terms, that cycle is 1 second. So we want to understand in this case, in a megahertz, there could be a million functions or operations or actions of some type that could take place within a cycle within 1 second. So a million operations in 1 second. You might have also heard, gigahertz, which would be a billion, 1 billion operations per second. This also has a lot of relevance when we talk later about CPUs, because most of your CPUs nowadays are 2 gigahertz, 3 gigahertz, or so, and so forth. But that's the kind of terms that we have to start with. Then what we'll do is, in order to determine our bandwidth, we need to understand how many megahertz something has or is capable of times the number of bytes that it has. Okay. And in the mathematics of that, when you multiply megahertz times the bytes, then you're going to wind up with your bandwidth down here. Okay, so by way of example, let me just go ahead and show you how this might all look. So if I have a PDF document here, which I'm making available for you up on www.nuggetlab.com. You can download this kind of as a reference point. And what we'll do with this is we're going to use this to kind of work through our math and calculate something. So for example, if I want to know what the throughput is, or the bandwidth is, of a PCI, which is, by the way, stands for Peripheral Component Interface, and it's one of the kind of interfaces that you can use for expansion slots. There are other kind of expansion slots we'll use down here as well, or take a look at. But there's also some older ones like ISA or ISA. They're all defunct and haven't been used for years. Anyway, the bus width is one thing we'll need to determine. Okay, and we'll multiply that by the bus speed in megahertz. So if 1 megahertz is 1,000,000 cycles per second, this would be 33 million functions per second. Then we would have the data cycles per clock. So there are certain technologies that will subtract from or add to the data cycles per clock. It's kind of a way of cramming more into a second than it might otherwise be able to do, or subtracting a little bit from it because of certain technical reasons. And then we would have the total bandwidth. This should be the mathematical result of everything we see over here to the left. So let's go ahead and take a look at that. In fact, let's go ahead and get my handy little calculator out. And what we have here is, let's see, we have 32 is the bus width, and this is the math that I'm going to show you here first is going to be wrong, and I'll tell you why in a moment. So I'm going to multiply 32 times, where's my times? There it is, times 33, and it's only by a multiplier of 1, so we don't have to do anything there. That says, 1,056. See, that doesn't look right, does it? It's supposed to be 133. Well, what you do with this is, well, you have to break the bits down here into bytes. Remember, a byte is 8 bits. So 8 goes into 32 4 times. So that would be 4 bytes. So it would be 4 times 33 equals 132. Well, you look at that and say, James, you're still not wrong. What is this? Some kind of new math you're trying to pull over on us? Well, okay, smarty pants. What this actually is there's rounding going on, as I mentioned earlier. For example, the bus speed is actually 33.33 megahertz. It's just that we kind of round it down to 33. So if I were to put that in there, then you could see that it would get to 133 something. Actually, let me clear everything out. We'll clear everything out here eventually. There we go. So it would be a 33.33 times our bus width of 4 equals 133.32. So that's a little bit closer. So you can see that. Now, you don't have to go through the math of all of these. I have done it for you, folks, with my crack mathematical skills. But we have a number of different bus widths and different technologies that I've gone through down here for you, and these have kind of all been pre-filled out for you, and we also have an additional chart down here that you can look at as well. We're not really talking about these quite yet, but we'll talk about those at a future point in time. But these will identify the speeds of all the bandwidth for you. Now, you might look at this and say, oh, great Scott, I'll never memorize all of this. And that's probably true. In fact, I haven't. But what you do need to know for A+ exam objective purposes is you probably need to know, at least in generalities, is the PCI, here, faster or slower than, I don't know, PCI Express. You need to know those kinds of basics. The thing where you might need to get a little bit trickier here is if you're looking at PCI-X at 66, and then you're looking at something else like, this one down here, PCI Express 2.0, well, they're real close in speed, and so there you might need to make a little bit more of a distinction. I still don't think you have to memorize this whole thing, but at least have a general idea for which kinds of bus types are faster than others. Now, and again, we'll take a look at this again visually here in a moment, but you've seen pictures of motherboards in the past in this series, and we've looked at PCI slots of various types and other types of slots. Well, those slots have a certain amount of throughput that they're capable of, or bandwidth that they're capable of. Also, I think it's important to understand that there's a difference in the bandwidth between the theoretical versus actual. For example, we saw that PCI slot is capable of 133 megabytes per second. But if I'm putting a network card in there, there's no way in the world it's going to get 133 megabytes per second throughput because of several limitations, including the fact that network cards are normally capable of only 10 megabits per second, or 100 megabits per second, maybe a gigabit per second, but nowhere near 133 megabytes per second. So now I've got to explain the difference between megabits and megabytes per second, okay? Let's take a look at it this way. A megabit, notice the lowercase b, per second, okay, means that it's capable of 1,000 bits per second. Okay, now that correlates to the bit that we see over here. So if I have 8,000 megabits per second, what do you think that's going to equal? Well, 8,000 megabits per second is actually 1 megabyte per second. Okay, megabyte per second. So it's the same kind of a 1 to 8 relationship with megabits and megabytes that we have with bits and bytes that we see over here. Alright, I decided just to pause recording for a few moments there and just throw together a little chart for you. You don't need to memorize this at all. This is just for your own reference, and you can take it or leave it if you want. It'll still be available for you up on nuggetlab.com. But this will just be a conversion for you for, where was I? What were we talking about here, for example? A megabit per second. See, that's 1,000 bits per second. And a megabyte per second. See, that's 8,000. And then if you want to convert between one or the other, there's also a bit per second and byte per second conversion formula that you can use there if you want as well. Now, of course, I've been discussing the various bandwidth and some of the technical details about these various expansion bus slots, but here what I want to do is to identify some of the specifics. Even though we've seen these in photographs in the past, now we're going to take a look at some of the details about each one of these types of slots, such as the PCI Express slot, which we see right here. These light blue colored ones are on the motherboard that I'm recording with right now, and we can see some distinctives about these, especially when you compare them to the other slots. All the other slots that we see in this photograph are PCI Express. These are the two types of slots you're likely to see on any computer made in the past few years, in fact. You might still find AGP slots as well, and I'll show you that in a separate photograph, but that's kind of a fading standard because they're not in any new motherboards anymore. But anyway, when you compare this, take a look at the distance from the back of the motherboard. This is where the bracket's going to be when the motherboard's inside the case. That's where you're going to screw in the bracket, and this is the back of the case. Notice the distance here between the back of the case and the beginning of this slot, and then compare that to, for example, these PCI Express slots. Notice that these PCI Express slots are in a little bit further than these are. Okay, so that's one visual distinctive so that you can identify a PCI slot. Also, notice the various contacts here. Each one of these little black holes that you see here are slots that you see in the actual card itself, or actual slot itself, represent a place where there will be a contact. Notice that over here, there's a lot more of those contacts in, roughly the same space, okay? So there's quite a lot more contacts there. That's another visual identifier. Then another one that you'll see here is take a look at the key that we see right there. The key is a raised position in the slot that will prevent you from putting the wrong kind of card into this slot. For example, if I were to take a PCI Express video card that would normally fit in this slot, it would not even fit in this slot. Why? Number one, because of the distance between the bracket and the beginning of the slot in the first place, but also because if I tried to put it in here, the PCI Express card does not have a gap in the actual card in this corresponding location. See, the card that will fit into this, that should properly fit into this, will have a gap. A PCI Express card will not have a gap in order to be able to fit around this keyed position, thereby preventing me from making some kind of a boneheaded mistake. Although I'm sure that if I really try, I can figure something out. But at least on a casual attempt at inserting one kind of a card in the wrong kind of slot, you should not be able to do that. Now, there's another thing to note here about this key. The key in the forward position that we see right here identifies this as a 5 volt. That's kind of hard to see. Let me right off to the side here. This keying position identifies that as a 5 volt a slot, okay, so that it can supply 5 volts of electricity to any of the expansion devices that we put into it. And if I were to take a look at a PCI card, we would see how it would fit into that. For example, here I've got an older network card that I've got. I think it's only a 100 megabit network card, and we can see that over here on the actual keying that this is open. So that will fit right over the top of that 5 volt slot. So therefore, by looking at this, I know it's a 5 volt card. Notice that this location right here, however, is blocked. It's got that opaque, material or whatever it is here, the substrate, and it will not allow this card, this 5 volt card, to fit into a 3 volt slot. You see, there are also 3 volt slots that could also be used. So a 3 volt slot would have a notch approximately, somewhere back in here. All right. Now, a lot of motherboards as well nowadays will be able to kind of intelligently determine when you insert a card in there what kind of voltage it's designed to take and apply the proper type of voltage. But by keying, you can kind of hard code it into using one type of voltage or the other. And then by way of example, what we see here is a PCI card that is actually a TV tuner. And what I could do is I could just plug in my coax cable here, my household coax cable, to watch television signals through this tuner right here. And by the way, the Winter Olympics are on this week, so my video production might slow down dramatically. Anyway, what we have with this is it's a PCI card, but it's a universal card. Let's zoom in on these contacts down here. As we take a look at this, notice we have two different notches. This one's for the furthest away notch, which is the 5 volt that I already showed you. Okay, but I could also put this into a 3 volt only slot, and this would then allow it to run the same card on 3.3 volts. And if it has the ability, most of these cards will be able to default to the lower voltage if possible. So for example, I could put this into my existing motherboard, which is notched for 5 volts, but a lot of times motherboards and devices nowadays are also able to intelligently determine whether it can run on lower voltages, and then it would. And then by way of example, I have a photograph here of a PCI card. This is actually a TV tuner card where I could plug my coax cable in right there and watch TV all day. By the way, the Winter Olympics are on at the time of this recording, so my production might slow down dramatically. Anyway, what I could do with this is, notice that it's got a couple of different notches down here. Now, we've already seen one of those notches in my existing motherboard, which is notched for 5 volts. So, if I were to put this in there, it could use 5 volts. But remember I said just a moment ago that it's also sometimes able to intelligently determine the lower voltage that it could possibly run on. With this card, it's a universal card that could also run on 3.3 volts. Okay, so in this case, it probably would run on only 3.3 volts. This card would also be able to be put into a slot that was hard-coded for 3.3 volts and then only run on that. And then here I've switched over to an old server that I have. It's decommissioned now, but you can see in this one that I have my traditional slot right here, my PCI slot, which is notched for 5 volts. Notice that I also have a couple of other types of slots, however. This is a 64-bit PCI slot, and you can notice that in terms of where the slot starts right here, it's exactly the same. This is where the 32-bit slot ends, and this notching right here is only to designate the end of the 32-bit portion of this slot. But then if I have a 64-bit card, then I could put that in here, and it would use these remaining contacts throughout the end of the card. And then this is where the 64-bit card would end, right here. At least where the slot would end. Sometimes the cards will actually extend a little bit longer past the end of the slot. And these 64-bit slots are capable of running either 32-bit cards or 64-bit cards. In fact, by way of example, let me zoom in a little bit here. You can see that right here, I've got just that going on. Here I've got, I don't even remember what this card is right offhand, but it's a 3.3 volt 32-bit card. There's a 3.3 volt notch right there, and you can see that the card ends right here in the 32-bit length. Okay, so that's what we've got here. We're able to use the backward compatibility capability of this type of slot. And then here I wanted to zoom in a little bit further. We're like at almost the microscopic level now. And this is a PCI, I don't know what happens with my pen here, but this is a PCI X slot in actuality. Now I want to bring up something about that. First of all, I'm not confident that the PCI X slot type is going to be a big issue on the A+ exam, but it's easy to learn about, so I'm going to go ahead and address it here just in case. And the PCI X is always 64-bit. That's why this is a 64-bit card that we've been looking at here. Okay, as we go back out even further, now at 30,000 feet here. So as we take a look at that, if we go back to our document, notice that here PCI X is always 64 bits all the way down through, and you're normally going to see that in servers. It is backwards compatible to all previous versions of PCI, but it is not compatible with PCI Express because the notching and the location of all of this is going to be different. And then that takes us back here to our PCI X slots. Okay, and remember, those are normally found in servers, 64 bits in length. May not be part of the A+, but it's important to know anyway, just in general. And then, now let's move on here to PCI Express. The PCI Express slot has a different form factor, and it overcomes a lot of the limitations of traditional PCI slots. And to identify some of those problems, let's return to this PDF where, let's say that even on the most high-end server, you had a PCI X 533, and it was 64 bits at this many megahertz, and you were getting 4.2 gigabytes per second That's a massive amount of throughput. But electrically speaking, in terms of the engineering and all of that, it's very difficult to get any faster than that. And one of the big reasons for that is that all of the data here has to work in parallel. 64-bit widths, all the data has to arrive at the end of every lane at exactly the same time. It's kind of like this. Let's say that I had a fan club. Okay, I know it's hard to believe, but let's just say that I had a fan club, and there was all kinds of people that were members of my fan club, and I called a meeting down at Applebee's, and I said, hey, everybody, come to the James Conrad fan club, and everybody came plowing through the door, 64 lanes of traffic at a time. Well, they couldn't really do that. It'd be very difficult to synchronize the arrival of everybody pushing through the door at once. There'd be some kind of stampede, and the cops would come, and an ambulance would be there, and all that kind of stuff. But again, for the electrical engineers, it's very difficult to get this parallel timing just right, and they pretty much reached the limit of what they could do with this technology. Plus, remember, this is normally going to be on a server. Even on a consumer-level PC, you're not normally going to get that. So as I scroll down here, let's take a look at PCI Express. What do we have here? One puny little lane of traffic. And we have 2,500 megahertz and 0.8 cycles per clock, and then we would have 250 megabytes per second. But remember, that's only a single lane of traffic. But in terms of the electrical engineering of this and how engineers are able to make all of this work, it's actually much simpler. It could also result in cheaper devices than if we were to try to push this to an even further limit. So with something like this now, we don't have 64 lanes of traffic where everybody's all arriving at once at the Applebee's through the front door, but we would have only a single lane of traffic, a single file line. Everybody has to line up behind each other. But guess what? We can all come through 2,500 at a time, pretty much, is kind of how we're looking at this. So we'd have to kind of put a revolving door in the front of the Applebee's, and the people would just come flying through, and in 0.8 data cycles per clock here, and we would then get 250 megabytes per second. By the way, just in case you wonder about whether I would ever actually have a fan club and anybody would join it, I'd like to let you know that one of our CBT Nuggets fans did email me recently saying that he started a fan club for me. I was very, very flattered. And then I went to the fan club and looked at it, and guess what? Do you know what the membership of this fan club is? 1. Oh, well, at least somebody tried. And then you can see that you can now also put additional lanes. It's not bit width. These are lanes in PCI Express. So it's somewhat analogous to a 16-lane highway or 32-lane highway. And also, this PCI Express that we see here, this is the initial version of PCI Express. Most of the computers that you see nowadays are going to have PCI Express 2, which, as you can see here, is twice as fast as the original. And so our throughput is getting pretty fast there. And you might see up to this level on the A+ exam. However, now, in terms of the technology, newer motherboards coming out as recently as late 2009 are having PCI Express 3.0. In fact, the motherboard that I'm recording on right now has this level of PCI Express. And look at that. That's a screaming, what is that? 32,000 megabytes per second. So that'd be 32 gigabytes per second. That's really, really fast. And let's also calculate the throughput of this. Let's make it simple and go back up to the very earliest level of PCI Express. And if I bring in my calculator here, you might say, well, wait a minute. Before we were kind of dividing by 8. How do you divide, 1 by 8? Well, you still do that, actually. So what you would do is you'd take 1 divided by 8 equals 0.125. And then you would multiply it by the megahertz, so that would be, where's my times? I just had, there it is, times 2,500 times 0.8 clock cycles, so that would be times 0.8 equals 250, and there we can see is the exact result of what I just calculated, 250. Also returning to this, I want to point out that I've kind of emphasized the by 1 and the by 16 PCI Express slots. There's also a by 4 and a by 8 slot. Although you're not normally going to see those on consumer level PCs, normally you're likely to see those, however, on servers. And then as we look at the actual PCI type of device, PCI Express devices, we see this by way of example. This is specifically a serial ATA card, where I can plug in an additional internal serial ATA card into this connector, or I can plug in an external, or an eSATA. Okay, that's what that is. eSATA onto the external. They use different types of connectors. We'll look at that more when we talk about storage at a future point in time. And then we see the actual connector for our PCI Express by 1 slot. You can see right here, really narrow and small. Doesn't look like it's capable of much, but it's more than enough for the throughput of even 2 of the drives that might be attached onto this. And then, of course, again, is the notching. And then PCI by 16, you're very often going to see used for video purposes. Here's a little bit of an older card, but it still works, and it's still the same in principle here. And you can see that again for this one, it's a much longer slot. The first part of this looks the same as the by 1. Okay, all of this distance from here to here up to the notch looks the same. But then you have all this additional contacts that we have here all the way through the by 16 space. And then you'll have this item right here, which is used to lock in the card. This is going to be very similar to what we saw for AGP, and we'll talk about that again here in a moment because I haven't addressed that yet. But both AGP and PCI Express by 16 video cards will use something similar to this, which will have a little tab on it that will lock this into place so that it doesn't kind of work its way out over time. Here then I've gone to another motherboard where we see a couple of PCI by 16 slots here, and what we can do with these is you could just put in a single video card, and for most consumers that's going to be just fine. They'll just put it into maybe this slot right here, and that'll be it. The section at the front of that video card where you put the notching in, that's what I was talking about right here. And you can see, I don't know if I can zoom in far enough for this, but you can see that there's kind of a notching that goes into this. And this notch right here would then extend over that little extended portion of the card, and it would lock it into place. In order to remove this card then, what I would have to do is to put pressure on this little lever right here to bend it back so that this could then be exposed. And you may also have to push this out here as well because there's an interlock right there as well. But you can sometimes have to use 2 hands to do it, but you could pull that off and then remove the card if necessary. And then the other thing that we see here is something for NVIDIA video cards called SLI. Actually, it's right there on the card, on the motherboard here as well. It's called SLI. Okay, and what this allows you to do is that you can put one video card here and another video card here. You can then bridge the 2 cards together and send the output through one of the video cards out, and you'll get twice the video performance, at least to the theoretical maximum, out to your video, and it's very useful for high-end gaming or high-end graphics and the like. Also, what you would do then is you have to tell the video cards that they're going to be then combining their processing power and sending out through a single card, and that's what this item right here is on the motherboard. They don't always appear this way, but you would turn this one direction in order to identify that you want to use a single video card, and another direction to identify that you want a dual video card. So you would just bend these tabs back here and flip this around. You can see here it says dual, and then over here it says single. Right now it's set for single, so I'd flip that around for dual. The other thing you could do is a lot of those video cards will have on the top of the video card a certain slot where you can put a connector. And this if both cards are installed right now, I would take that slot and I would just put a special connector over the tops of both of those, and then that's how I would get my SLI connection. You can also use ATI devices as well. This is just 2 competing vendors. ATI uses a same or a similar technology to SLI, but their branding is called Crossfire instead. And then just briefly here, I wanted to show you an actual photograph of that connector I was talking about earlier. So you have 2 video cards in here, and then you just put this connector between the 2 of them to bridge them, and then you now would have SLI, or again, there's a similar item for Crossfire. This can be done either through the motherboard, through the first connector I showed you, or through something like this, which you put on top of the video cards. Okay, and then returning to our whiteboard here, let's just take a look briefly here at this TV card item. This does appear on the exam objectives, although it kind of baffles me why, because it's not really that big a deal. I mean, you plug it in and it works, right? The only thing I can think as well, though, is that you might need to come up with some additional, let me start another whiteboard here, some additional things to keep in mind. So, for example, if this is the PC card, or, it could be a PCI card, or, it doesn't really matter the interface. But if this is the card, then how does that connect to your actual TV? Well, this could be just a coax cable. Actually, that'd be COAX, wouldn't it? So that could just be a coax cable. And if you just connect it directly like into the wall for your coax from your cable provider, that's going to be an analog signal, okay? However, you could go another way as well. And with this, you could plug that into a digital tuner of some kind, a digital, depending on your cable provider, could be called a digital box or just a box or something like this. And this could do a couple of things. It could give you a digital signal, obviously. And if you also pay a little extra money for it, you can also get HD signals through it. Now, once you send HD signals through this card, if it supports that, then you could get HD signals out through your computer monitor. However, HD goes up to 1080i for television signals, and most monitors may not go that high, so it kind of could be a waste of a feature. You might have to upgrade the monitor to be able to support that. And then kind of the line between monitors and televisions is kind of getting blurred now, because I know some professional photographers that will actually use what's classified as a television, but they plug it into their computer, and they can still get 1080i or 1080p out of that monitor. But of course, out of something like this, a television signal would still only be 1080i, which means 1080 interlaced, and it's not quite as good as 1080p. Although most mere humans probably could not tell the difference. Now, from a consumer level, there's another thing that the user could do that they would not have to spend any money on a digital box, because this could be, this could be $10. I'm just guessing here, and then for HD that might be another $10. So there might be a total of $20 or so to get all of these, fancy things. They could also put, and I'm just gonna kind of run out of room here. They could also just put an antenna up, okay? And a lot of these devices come with a small antenna. It's not like those that you stick on your roof or something. A small antenna that will be able to receive HD signals at no expense, because these can be broadcast now. The problem is, unless you're in a place where you can get really good reception, they might not be very clean. And in addition, if they don't receive HD signals either, then they will probably still just get over-the-air broadcasting. And for that, they might complain about a snowy picture. Okay, that's very often what they're going to see if they have a snowy picture. They could also get a snowy picture through coax analog, especially if their TV signal has been split off many times. Maybe they have a family room and a living room and 2 or 3 bedrooms, all that have coax, and every time you go to a different room, you may have to have split that, so they might be getting a weak signal. So again, they might be getting a snowy signal through that, which of course, but that actually might be welcome for the Vancouver Winter Olympics this year, because they're not getting any snow up there. So the snowy signal might be all the snow that you can get. In fact, they're even trucking in snow for the skiing events and the like. But if the user is complaining of a snowy picture for their digital TV tuner card, or their TV tuner card, then the only other thing that you could do is either call the cable company and see if they can do something for you. And one of the things they might do is to be able to put an amplifier on it, or you can go to almost any store, Radio Shack and so forth, and get coax signal amplifiers that you can plug in as well. But all of this stuff that I'm telling you here is probably way more than you would even need to know for the A+ exam. That's my guess anyway. I'm just, since they had it on the exam objectives, I thought I'd go ahead and cover it. And then I don't really have a whiteboard for this because it's real simple and quick information. But your TV tuner card can also be used as a capture card. There's usually external inputs so that you could plug in some kind of an external device, like a DVD player, a VCR, some other kind of a audio-visual device, and that TV tuner card could sometimes, depending on what brand and manufacturer and what features it has, it could capture that. Or you could also get a dedicated capture card, but we don't really see a lot of call for those things, but those things also do exist with I/O to send or receive video and audio signals. And then for video cards in general, the more memory they have, the more capable they usually are of displaying complex graphics. A lot of video cards now have somewhere in the gigabytes of video memory, and as such, they're able to perform very highly. You may see some older ones that only have 256 megabytes or 512 megabytes, and if people are only doing normal office routine kind of functions, that should be fine. But if they're doing gaming or something like that, they're going to want probably at least 512 megabytes, if not a gigabyte or more. Now that TV tuner card might be a PCI Express card, it might be a PCI card, and there's one other that's not really on here, and it's becoming increasingly popular, and that would be just a USB. In fact, I think did I go to that website? I think I have a website where I showed that. Oops, there's my guilt again. Okay, that's right here. There it is. This actually I've got in the back of my own computer right now. This is actually the one I've gone to because it's smaller and easier to manage, and I don't have to use an expansion slot for it. But you can see here that it's USB, and then there's the connector for your TV source. Now let's also talk here about AGP cards. These are something that were video cards in years past. In any current new motherboard, you're not going to see AGP slots. They've all gone to PCI Express. But you may still have customers that have AGP video cards and slots in their motherboards. And in fact, if you go to the electronics store and you try to buy a video card, almost all the shelves of video cards will have PCI Express by 16. You might have one or two video cards that are AGP on the bottom left shelf for those holdouts that just have to stick with AGP for some reason. AGP, I've got that also on our little PDF document here, and you can see that that's gone through several iterations. One thing that's not on here because it was never really an A+ exam objective anyway in the old days is the AGP Pro, but you see different speeds and things that are available through this. But you can see that the PCI Express is going to be much more efficient and faster. Even on the first version of PCI Express by 16, it's good for 4 gigabytes per second, whereas the fastest consumer level AGP at 8x was only about half that speed. Now I had to dig back in my archives to find an old motherboard here, but I found one, and this one's got an AGP card on it that you can see right here. Okay, actually an AGP slot, excuse me, that you can use. And if I zoom in a little bit further on this, it's too bad it's black in color because it's a little bit harder to see. But there's the actual notching as well that appears for this item. And I'm kind of going to outline this. And this is similar to what I showed you earlier with PCI Express. It would lock the card into place, and then in order to remove it, you would apply pressure in this direction, and then you would push your thumb against it, and then you could work the AGP card out of that slot. And then here's what one of the AGP video cards might look like. This was one of the last ones that I had purchased, and you can see that I had dual video out with this. This was really a hot feature back in those days. And then you can see something about what the connectors look like here. And then again, there's this tab over here for the retention that you would use to insert it into that slot, and that's where the tab would then lock onto place. And then this is what it looks like from the back of it, so that you can see, and I'll move this in here again, zoom in a little bit further. This is where that little tab is locking that card into place. That's one side of it. And then the other side of it would be over here. This is the front side of it. And you can see the little tab here where you can push this back with your thumb and then release that tab that appears right here. And then before I move on, I would like to point out that you may have a customer that comes to you with a PCI video card, not PCI Express, just a plain old PCI. These are, again, largely defunct, but they may still appear sometimes. And so if you want to replace that one, you may have to look for a used one on eBay or something like that, because you don't see those very often, in favor of the PCI Express, or if they're still with an older system, maybe AGP cards. And then we have a couple of other kinds of older cards as well, or other slots, older slots. That would be an AMR, or an audio modem riser, and a communications network riser. Let's go ahead and address those here as well, where I've got a whiteboard just for those items. These, again, are kind of antiquated. I'm surprised that these are on the existing exam, but nevertheless, it's one of the exam objectives. Here, AMR, like I said, is an audio modem riser, and it does just that. It provides audio and modem capabilities to your card, to your motherboard. And if we take a look at that, then we'll see here again on this older, antiquated motherboard here that we have an AMR slot right here, okay? And then we just put in that card that would provide modem capability and audio capability. And that's pretty much it. So just so you're aware of what that is. And then, like I said, you may also see a communications network riser, which is very similar in the kinds of the form factor and what it does. And this gives you a communication network riser that provides digital audio, so it's going to be better than the analog audio that we got with the AMR. And it also could provide network communication, so you might have a network card integrated into that as well. And then another kind of card you might see would be something called a riser card, or a daughter card, okay? Very similar in their functions. And what goes on with these things, let me just start a different whiteboard here, is that you would have, let's say you'd have your motherboard here, and we're just looking at the thin edge of the motherboard right here, and then you might have some expansion slots back here and stuff like this. And you could only fit in, so many of those, especially in smaller form factors, such as micro ATX, NLX, something like that. So what would happen here is, since you had a limited space, you could put in a daughter card here that would come up to the full height of the case. For example, maybe this is my total case size. And this could be a very small case. And then now, instead of having to go left to right with a bunch of different cards, that I don't have room for, I can now put slots on the riser card. And now I got an additional PCI slot there, an additional PCI slot there, an additional PCI slot there. Hopefully they're actually neater and cleaner than what I've drawn. And then now these cards would actually be able to fit into these slots, and these slots right here, the cards, would be parallel to the motherboard itself, and it's a way of maximizing the vertical space in the card so I can give myself a little bit more expansion. And then I just searched the internet for a picture that would probably illustrate this a little bit better than I could draw it. And here we have a single slot, but out of that we were able to put a daughter card, also known as a daughter board, and this would have 2 PCI slots on it, that then those cards would be parallel to the motherboard, as you can see, if you were to insert something in there. Now, just a moment ago with audio modem risers, I mentioned the word modem, and let's go ahead and address that again just real specifically here before we conclude. A modem could be a device that attaches through the serial port of a computer. Those are the really old ones. We don't see those very often anymore. Or it could connect through any expansion slot, such as PCI. You might even find some that are PCI Express. Okay, something like that. You definitely would see some older modems that were ISA, but that's not even part of the exam objectives anymore because ISA is very much defunct as an interface standard. And then finally, you may also see some modems that connect through USB connections as well. Modems, generally speaking, are pretty close to being defunct in terms of their practical use. Nobody really uses those anymore very much, but they are analog devices as opposed to digital devices. That means they depend upon some kind of a variance in electrical signaling. And what happens is they transmit data over wavelengths. Okay, that's why when you hear a modem connecting, it makes a big old screeching sound. I won't try to duplicate it here for fear of the fact that you'll will lose your business forever. But they're very annoying screeching noises, and very often they only do that during the initial setup. But what they'll do is they'll transmit data. This could be anything. You could be transmitting data to get onto a network. For example, in the older days, and I mean 10 years ago or so, I used to travel for a company that every night we would have to connect to the home office using a modem, and we would do it using the phone lines in the hotel. Once we'd made that connection, it was just as if we were on the local network back in the office, except that we were limited to the very slow speeds of that modem. And in fact, we had a bunch of scripts and things we used to have to run. It might take 10 minutes just to log on using our modem back in those days. These are very, very frustrating. And so, as I mentioned, they're very, very slow. These also use plain old telephone service. So you would not be able to plug, you would take the modem and it would be inside your computer. It could be in a laptop, could be in a desktop computer of some type. And then you would plug in an RJ11 phone jack into the back of the modem, and then the other end of it you would plug into the wall outlet where you would have your phone. Or if it was in a hotel, it would very often they would have a modem jack that you could plug that in as well. That was important because a lot of PBXs and hotels and things use digital phones instead of analog phones, so you'd have to plug that into an analog jack. Wow, this stuff's all really old. I feel like I've gotten a Wayback Machine, and I'm gone back in history here. Anyway, so you would use these things to then plain old telephone service, which we refer to as POTS, to be able to make these connections. And again, it would be just this analog data as opposed to digital, which would be zeros and ones. Instead we would use this kind of data that we would use instead, this analog data. This has also largely been replaced by cellular and VPN. For example, we use Verizon in my business, and so we have a Verizon wireless card, we call it, and we just plug it into a USB port, and it puts us on the wireless provider's internet. So we actually use internet. Once we've got that internet connection, then we connect to a VPN to connect to our home office. And this would be virtual private networking. What this allows us to do is to take a conventional internet connection. Let's say that this space here represents an internet connection, and then you would be able to establish a VPN in that internet connection. Oops, that would be a VPN, wouldn't it? And this would be an encrypted tunnel inside of your normal internet connection, and it would be encrypted and no one could then decipher it. So it's pretty pretty well generally regarded as secure. Whereas with analog modems, the only security you really had was there was a dedicated single line connection, say back to the home office. It was possible that someone could tap into it, but generally it was a point-to-point connection between your computer and the home office modem bank where it would establish that connection. Somewhat secure, but not very, because it's still subject to wiretapping. Whereas with a VPN, even if someone intercepts our signals, it's still generally considered secure because it's encrypted. In this nugget, we discussed buses. We started off with a discussion of the various terms, such as megahertz, clock cycles, and the like, and this was important in determining the overall bandwidth of a device. We took a look at PCI devices, which are still found on new motherboards, but which is going to be somewhat of a disappearing standard as time goes by because we are now mostly using PCI Express. Also, PCI X, which is going to be normally found in servers, and then, of course, as I mentioned, PCI Express, which is really good for now and for the future because it's a pretty good standard which allows a very high degree of throughput. Also, we took a look at AGP, which is the Accelerated Graphics Port. There's several different iterations of that, but that's also something of a disappearing standard. And we took a little discussion about TV cards as well. We talked about audio modem risers and communications network risers, which are still possible to see those in some new systems, but those, again, are only going to normally be found in really small form factors, so you can get more expansion out of those devices. And then there's the almost defunct modem, which you still see in use in a lot of organizations that have not yet upgraded to other technologies, but that's largely fallen to the wayside in favor of things like cellular technology and or VPNs. Well, I hope this has been informative for you, and I'd like to thank you for viewing.